Welcome to video 2 for this unit on introducing exponential functions. In this video, we're going to focus on defining exponential functions. The situations we have looked at are functions because any value of the independent variable corresponds to one and only one value of the dependent variable. Exponential functions are functions that describe exponential change. Earlier, we used equations to represent situations characterized by exponential change. For example, suppose C is the amount of caffeine in a person's body t hours after an initial measurement. For each time t, there's only one value for the corresponding measurement of caffeine C. So we can say that C is a function of t, and we can write this as C equals f of t. If there is an initial measurement of 100 milligrams, we can use function notation to model the change in caffeine levels. F of t equals 100 times 9/10 to the t. We can use this function to analyze the amount of caffeine. For example, when t is 3, the amount of caffeine in the body is 100 times 9/10 to the third, or 100 times 729 over 1,000. Which is 72.9. The statement f of 3 equals 72.9 means that 72.9 milligrams of caffeine are present 3 hours after the initial measurement. We can also graph the function to better understand what is happening. The point labeled P, for example, has coordinates approximately 10, 35. So it takes about 10 hours after the initial measurement for the caffeine level to decrease to 35 milligrams. A graph can also help us think about the values in the domain and range of the function. The domain of the function, the time in hours, includes non-whole numbers because the body breaks down caffeine continuously over time. The domain also includes negative numbers, which represent the time before the initial measurement. The range of this function also includes non-whole numbers, since the measurement can be a fractional amount. But the range does not include negative numbers, as a negative amount of caffeine does not make sense in this situation. When we calculate the average rate of change for a linear function, the value of the rate of change is the same for every interval we pick. When a linear function is represented by a graph, the slope of the line is the rate of change of the function. Let's look at an exponential function g, defined by g of x equals 2 to the x. Notice that the average rate of change for these intervals are positive but not equal. This is due to the growth factor of the exponential function. If the function represented exponential decay, the average rates of change would be negative. Unlike a linear function, an exponential function does not increase or decrease by the same amount over equal intervals. Instead, an exponential function increases or decreases by equal factors over equal intervals. What does that look like? If we graph g, we see that each time x increases by 1, the value g of x doubles. We can show algebraically that this is always true regardless of what value x takes. The value of g of x when x increases by 1, or g of x plus 1, equals 2 to the x plus 1. Dividing g of x plus 1 by g of x, we have 2 to the x plus 1 divided by 2 to the x, which is 2 to the x plus 1 minus x, or 2 to the 1, which is 2. Thank you for watching video 2 of 4 for this unit on introducing exponential functions.